Hi everyone, welcome to our live stream. We have a really special event for you. We have a panel of experts who are going to celebrate the first year of Webb Science with all of you, our Webb community sites all across the country. And so with me today, we have 4 experts. We have Brian Haller from the Space Telescope Science Institute. We have Emily Rickman from ESA and the Space Telescope Science Institute. We have Christine Chun from the Space Telescope Science Institute. And we have Taylor Hutchison from NASA Goddard. And today we're going to talk about what JWST, what Webb has been up to for the past year, and some of the science that really excites all of our panelists. So I am going to start sharing my slides here. And I would like all of our panelists, if you could come in one by one and tell us a little bit about this. Introduce yourself and tell us about the science that really excites you in your area of study. We'll start off with Brian.
All right. Hello, everyone. I'm Brian Haller, and I am a solar system scientist at the Space Telescope Science Institute. I want to talk to you about some of the exciting images that we've taken over the past year and some of the exciting science that's been done as well. So if we go to the next slide. Thanks. So some of the big questions in solar system science, of course, relate to, how did we get here? How, the composition of the original solar nebula, how that formed the planets, how that formed the minor bodies across the solar system, and we're beginning to finally be able to get a handle on that by going to longer wavelengths with the James Webb Space Telescope to see some more of the components that make up the bodies that we see all the way out to Pluto and beyond. And another question on the next slide. Right, how did the orbital structure of the solar system evolve? This is a very big question. It has, even has to do with how water may have come to Earth from small bodies in the outer solar system. We have this period of planetary migration that disrupted the entire solar system and put the planets where they are today. And next slide, please. And more immediately, the things that we can see today, how are the objects that we're seeing today evolving? What are those physical and chemical processes, right? When a comet comes in to the inner solar system, how does that the coma that comes off, the material that comes off. What does that say about the original composition of those objects? We have objects like Io that are very, Io is special. It's very volcanically active. Anytime we send a spacecraft by it, there's a volcano going off. We've also discovered rings around small bodies, which is unexpected. They're not fully spherical. What's the process that maintains those rings? And of course, clouds in Titan's thick atmosphere. There are so many questions about things that we can study in real time. It's not all ancient history. Next slide. And of course, which of the objects in our solar system have potential astrobiological importance? Right, obviously, the Earth is here in the center because we know that life exists on Earth, but there could be life on other objects such as Mars and Europa, under the ice shell of Europa, or in the interior of Enceladus in the top right there, or on Titan. And we can begin to explore some of those bodies in more detail with the James Webb Space Telescope. Next slide, please. And this is one of my favorite images so far. This was one of the um, one of the early images of Jupiter from last July. Um, and what I particularly like about this is an inverted image, right? So darker things are actually brighter, but I've inverted to show the this band across the top here that's separated from Jupiter. 400 years ago, Galileo turned the telescope to the sky, and Jupiter is one of the first objects he observed. And now, over 400 years later, we are still finding new things. That band, which we still can't explain right now, in a year later, is something that was newly discovered just in a very short amount of time by the Webb Space Telescope. Thank you for listening.
Okay, great. Yeah, thank you. Okay, next up we have Emily.
Hi everyone, my name is Emily Rickman. I work for ESA at the Space Telescope Science Institute, and so I work in exoplanetary science. So I wanted to highlight some of the exoplanet science that JWST has enabled over the past year. And this is actually what I'm showing here is an artist's impression of one of those systems that we looked at. So it's just an illustration, and unfortunately we do not get images of this detail, but we do work with artists and the media to try and get accurate illustrations of what these planets may indeed look like. So if you go to the next slide, please, Kelly. So I'm going to highlight a couple of techniques that we use to look for exoplanets and to understand their atmospheres so that you can try and understand some of the figures that I will show. So if you click, it should come up with an animation. Excellent. And yep, so what we see here is a demonstration of what's called the transit technique. And so we look at a star, and as a planet transits in front of that star, we get a dip in the amount of light that we receive from that star over time. And the bigger the planet, the bigger the dip in the light. And so that's what we're demonstrating there. And we can use this technique to not only discover and look at planets, but to also look at their atmospheres. So if you click again, then what we see here is the same technique shown, but we're looking across different wavelength regimes there. So in the purple, green, and orange, we're showing different components of absorption features in the atmosphere of the planet that we're looking at. And this is a really powerful technique to understand the exoplanets that we're looking at. So that's the transit technique. And if you go to the next slide, we can also use what's called direct imaging, which JWST is also capable of doing for exoplanets. And so this really is, as described, it's taking a direct image of a planet next to a star. And what I'm showing here is an example from a ground-based observatory, but the same principle applies. So we don't want to look at the star itself. The star is extremely bright, lets off lots of flux. We're interested in what's next to the star, and which is really, really faint compared to the star itself. So the contrast that we're looking at is extreme. And so in the image in the left there, we have the star itself. In this case, it's Beta Pic that's behind what's called a coronagraph, which is basically just a mask to mask out the light of the star. And then we can look for planets around the stars that we observe, which is what that bright orange blob next to the coronagraph is. So we can get nice images, but we can also, again, look at these data to assess the atmospheric properties of the exoplanets that we look at. And so on the right, we're stepping through different wavelengths and the amount of light that we receive at those different wavelengths. So rather than the absorption of the light using the transit technique, this does the opposite, where we get the direct emission at different wavelengths across a wavelength range to look for molecular features and atmospheric properties of the exoplanets that we observe. So if you go to the next slide. So this is a wonderful press release from the first exoplanet that was directly imaged with JWST. So this is extremely exciting. So what we're seeing here is there's the wide field of view of where the star resides. And then in these four smaller images along the bottom there, we're showing 4 different filters or 4 different wavelengths, which correspond to 4 different colors of where we see the planet. So this star is hidden behind that actual white star that's shown in the images there. And then the planet is that bright blob that's next to the white star in each of the images. And so we have NORCAM in the first two images on the left there, and the two images on the right are using Miri chronography. The exciting thing about imaging is that we can look at things that are really widely separated away from their stars. So the transit technique typically looks at planets that are really, really close to their stars. So things on an orbital period of maybe a couple of days, whereas imaging planets, because of the nature of how difficult this technique is to look at things really close to the star, we typically look at things that are much, much further out. But the important thing is that we need both of these techniques to really comprehend the architectures of the exoplanetary systems that we look at. So similar to answering some of the questions that Brian was talking about before for our own solar system, but we can extrapolate this for exoplanetary systems as well. If you go to the next slide, please. So this is my favorite result from the past year of science with JWST. I'm extremely biased because I was part of the team that analyzed the spectra, and this was part of the early release science program for high contrast imaging. And what we're seeing here is a direct spectrum of an exoplanet or of a planetary mass companion. And so we have that wavelength along the x-axis there, and then the amount of light at each wavelength regime. And we see lots of really exciting molecular features like carbon monoxide and water and methane. But the really exciting feature shown here in this kind of green orangish color are silicates, and this was the first direct detection of silicates in an exoplanetary atmosphere. And so this is just really the start of what JWST is going to be able to do, and is really, really exciting looking forward. And if you go to my final slide, so what I've showed you in the previous two exciting results are from the imaging side, and this is from the transit side. So those planets were very, very widely separated from their star. This one is very, very close to its star. And again, using the atmospheric techniques I mentioned at the start to assess their atmospheric properties, we were able to detect for the first time, clearly detect for the first time carbon dioxide in an atmosphere of an exoplanet using the transit technique, which is what we see here. And again, this is from one of the press releases. And so this is just opening up a wide range of things that we're going to be able to do with JWST going forward.
Okay, great. Thank you, Emily. Next up, we have Christine.
Hi everyone, my name is Christine Chun, and I'm a scientist at Space Telescope Science Institute. I'm going to describe the research that people do to try to understand how planetary systems form and evolve. So this research sort of sits at the junction of solar system and exoplanet research that has already been described by both Brian and Emily. So Brian told you about objects in our solar system, and our solar system is relatively mature because our sun has an age of about 4.5 gigayears. Emily told you about exoplanets that JWST has been studying. These can have a wide variety of ages. And what I'll tell you about is studying planetary systems, particularly young ones, in which you not only have planets, but also remnant leftover materials from the assembly of the planetary system. So when I think of young exoplanetary systems, I have a picture like this in my mind. So you can see that in this particular picture, there is a Jovian planet here, which happens to have formed. There may be also terrestrial planets, as also shown, and there's smaller objects as well that could be analogous to comets or asteroids. And just like in our solar system, the number of planetesimals, comets, and asteroids is much higher in these young exoplanetary systems compared to our solar system now, maybe 1,000 times more. And so this leads to collisions between these objects, and they grind down and they produce dust, which we can detect with James Webb Space Telescope. So this really plays to one of the superpowers of JWST, which is the ability to study dust in our universe. And so the advantages of studying these dusty systems are really kind of twofold. One is that when we study exoplanets, we measure the mass and the radius of the planets, and that gives us some sort of sense of what the bulk density of the planet is. So we don't know precisely what it's made out of, but we have some idea that, maybe it's very heavy material or very light material. In addition, Emily showed you the beautiful transit spectroscopy, which probes the atmospheres of the planets and gives you some detailed idea of the chemical composition of the atmosphere. But that's really just the thin skin on the top of the planet. Whereas when we bust up the comets and the asteroids, we can get a sense of what the detailed chemical composition of those materials is and have some insight into what those things are made of. In addition, the dust grains act as kind of test particles. They're really sensitive to the presence of planets, even as small as Pluto. And so they can create structures in the disk that allow you to detect planets that you can't see directly. Next slide, please. So I wanted to make a connection to our solar system in that I showed you the picture of how these young planetary systems are dusty in the later phases. This is because there are collisions between different objects, and we have evidence for giant collisions in our own solar system when it had an age of about a couple 100 million years or so. So the different kinds of evidence that we see, if you look at Mercury, for example, the ratio of the mantle to the core is different compared to the other terrestrial planets. It has a very disproportionately large core. And so we think that it experienced a head-on collision which ejected the mantle of Mercury. Similarly, if you look at Mars, the northern hemisphere, you can see is smooth and it's actually at a lower altitude. And that's believed to be because it experienced a giant collision. And so you're seeing kind of a crater, a giant crater in the northern hemisphere of Mars. And then finally, if you look at Earth, the Earth-Moon system, we think that the way that the system was created was that a Mars-sized object smashed into the proto-Earth, and it was kind of a glancing blow. And so when that happened, essentially the core from the Mars-sized object sunk into the Earth's core, and the mantles for the two materials mixed, and then condensed to form the moon. Next slide, please. So I'm super excited about the really beautiful JWST observations of Fomalhaut. Emily showed you a beautiful picture, a chronographic image of a giant planet taken in multiple wavelengths. These are images of one of these dusty young planetary systems seen in multiple wavelengths. So the JWST observations are the sort of greenish ones on the left. And for comparison, you can see the Hubble Space Telescope image on the left in purple. This is visible light that our eyes can see. And then on the right, you can see the Herschel and ALMA images in yellow and red. These are longer wavelengths, and so they actually probe different size dust grains in different parts of the planetary system. So there's a couple of, I think, really spectacular things about this picture of Fomalhaut, and you can see how it reveals new things about this planetary system that have not yet been seen before. On the right-hand side, you see the central star at the middle of the picture, but the distinctive thing about the JWST image is that there's an extended nebulosity around the star, and this is dust that's in the region of the asteroid belt. And so this is telling us that there are actually asteroids in the system, and they're smashing into one another and creating dust, which we can see beautifully in this JWST image that we could not see in any of the other observatory images. The other thing that this Fomalhaut image shows us is that there is a gap. So you can see there's a dark lane in the disk. And we think that what's happening here is that there's a planet in the disk, and it's sweeping away dust in its orbit as it's going around the star. And so this is another case where even though we can't directly detect the planet, we know that it's there because we can see the impact that it has on the dust in the planetary system. I think next slide, please. So I just wanted to lastly share with you this beautiful composite image when you lay all those different images together. So on the left-hand side, you can see the ALMA image. This is the millimeter wavelength image, which represents the large particles. So that's like the reservoir of comets that live around this star that are crashing into one another and creating the dust. The blue ring is showing you the HST image, which is sensitive to fine particles, the little tiny ones that are the products of some of the products of the collision. And then underneath, you can see in yellow the JWST image. And you can see how much more sensitive it is, and that you can see not only those main rings, but then all of this dust, both interior and exterior to it. When you line them all up on the right, you can see how we can learn about the system in that it's much more active than maybe we might have guessed at first blush. So when we look at the system, we see that the large grains are actually slightly interior to the small grains. And this is actually consistent with our understanding of how the system works, which means that the small grains are actually sensitive to radiation pressure from this star. So the grains act as little tiny sails, and they catch basically the starlight, and they are blown out of the system by the starlight. And so that's why they look offset compared to the red ring, which is showing you where the dust grains were born from. So I'm super excited about this area of science, and I'm looking forward to all the other wonderful things that Webb's going to share in the next year.
Okay, thank you so much, Christine. And now we're on to Taylor.
Hello, hi y'all. I'm Taylor from NASA Goddard. So I'm actually going to take you to the other end of cosmic time. And so we're going to be talking about the first galaxies that ever existed that we're trying to find with JWST. And so what I'm showing you here is just my favorite cartoon depiction of the history of the universe, where we have the Big Bang on the left-hand side, and with time increasing to the right, all the way over to that little orange or yellow circle that I put us on. That's where we are. That's present day. And so a lot of the science you just heard kind of lives inside that circle over by present day. So where we're going to go, if you want an animation, press next. We're going to go over here. And so we're very close to the beginning of the universe, where we have the first galaxies beginning to form. And so what's really exciting about this is a really chaotic time in the early universe. And you can see this through simulations. If you go to the next slide. So in this simulation, we're kind of walking through this early universe towards, closer to present day. And so in this early universe, you have a lot of clouds of gas and dust kind of enshrouding and hiding these galaxies from detection. And so it's actually really interesting for a lot of different reasons. How did this time in the universe happen? Why does current day why doesn't it look like this now? How do we find these galaxies? Because as you can imagine, these dark clouds that you're seeing in the simulation, it's really hard to look through those. And so you really need something that's incredibly powerful, like the amazing abilities of the JWST, to really dive into this and try and peer into this, what we would call cosmic fog of the early universe. And so if you go to the next slide, so some of the ways that we've done this are, these beautiful massive images that we've taken thanks to the JWST. And these are essentially just massive galaxy fields. And so what you're seeing here is actually an example from a particular survey I'm a part of called SEERS, where in the very background, we have a really big footprint on the sky. So essentially just a lot of images covering a big portion of the sky, but not really. If you, hold your finger out at arm's length, it might be a tiny little dot on your finger. That's the portion of the sky that we're looking at. But we see in these little boxes, we're zooming in and in and in until we get to the little square on the bottom right. And that little fuzzy red dot is a galaxy that existed over about 400 million years after the Big Bang, so over 13 billion years ago. And so it took the light from that galaxy over 13 billion years to travel to reach our telescope, which is just kind of a really exciting and kind of wild. And so this is the kind of stuff that we're looking for. We're trying to find the most distant galaxies possible. And thanks to JWST, we're able to continue pushing this barrier and going even more and more distant and further away from us. And so something I was really excited about, if you want to go to the next slide, I think one of my favorite results from this year of science with this telescope is this beautiful spectrum. So if, in case you're unfamiliar, I like to describe spectra. It kind of describes all light that you see from a cosmic object. So I kind of treat it like a light fingerprint. And so with these light fingerprints, you can understand the chemistry of these galaxies. And so this particular light fingerprint is from a different galaxy that is also incredibly far away. And from all of this, we're able to understand the chemistry of these galaxies and the kinds of stars that live inside of them and what the black holes might look like, and a lot more science that can come out of it. And so it's really exciting. And this telescope is just kind of perfectly built for this kind of science.
Okay. So thanks to all of our panelists. If you are an official host site, you will have gotten a link that you can ask questions on, and you can also upvote other people's questions. And we are going to spend the rest of the time answering your questions. But as the moderator, I get to go first. And so I would like it if all of our panelists could maybe talk for a minute or so about their own science career path. How did you get to where you are today doing all of this really cool science with Webb? I don't know if there's someone who wants to go first. Go ahead.
I guess we can pick up the same order as before. Back in 2003, August of 2003, there was a very close approach of Mars to the Earth, one of the closest approaches in 50,000 years. I happened to be going to the library at that time, and on the end cap there are a bunch of library books on astronomy. So I cleaned it out. I took every book off of that end cap, and I was hooked from that point on. I knew that I wanted to be an astronomer. I didn't know which direction I wanted to go in. The planets always interested me. So I did take some detours to some neutron stars for a little in undergrad, but I did my undergrad at University of Maryland. And then in grad school at the University of Colorado, I found my way back to the planets, and I did my thesis on Pluto and other trans-Neptunian objects. And I've been at Space Telescope since that time. So that's my story.
Okay, great.
Yeah, I guess I can pick up next. So I was always interested in astronomy and astrophysics. I went to the University of Sheffield in England to study astrophysics, and it was there that I was taught a course by Professor Simon Goodwin about exoplanets. And I was like, wow, this is so cool. Like I didn't even really know about exoplanets at that point. And as part of my degree there, I spent 1 year studying at the Australian National University in Canberra in Australia. And that was the first time I got to get my hands on some, it was NASA Kepler data at the time, which is transiting exoplanet data. And that just blew me away that we were discovering planets and trying to understand these planets. And since that point, I just made it my mission to stay involved in exoplanetary research. So I finished my master's at the University of Sheffield, and then I then went to the home of the founding fathers of the first exoplanet that was detected around the solar type star, which is Geneva Observatory in Switzerland, and that's where I did my PhD. And working alongside Michel Mayor and Didier Queloz, who are the Nobel Prize winners in 2019. And they just taught me so much, and I was just so inspired by the journey into learning more about exoplanets and things. And then I was very fortunate after my PhD to have been awarded a fellowship by the European Space Agency. And so we have people who work for the European Space Agency, or ESA, like myself, who are based here at Space Telescope in Baltimore, because we are partners with Hubble Space Telescope and the James Webb Space Telescope. And then since being a fellow here for a couple of years, I then got the position I'm currently in as science operations scientist, and I am super grateful to be able to work with such incredible data every day. Yeah.
Hi. So I remember when I was 12 years old, going out with my dad to see Halley's Comet. And I think that those sort of experiences as a kid were very formative for me. My dad happened to be a scientist, and so, I thought that maybe that would be a career path that would be really interesting for me. When I went to college, I tried physics as a major, and I discovered that I didn't really enjoy it very much. And so, I looked over, down at the next building over, and was like, those astronomers look like they were having a ton of fun. Maybe I should go check that out. And so between college and graduate school, I switched the area of my focus. And I was super lucky to be really well mentored as a graduate student at UCLA by a professor there named Mike Jura, who is a really wonderful mentor and got me very excited in studying planetary systems. I was really privileged to, when I came out of graduate school, my timing was perfect for becoming involved in one of NASA's missions called the Spitzer Space Telescope, which launched, oh my gosh, I think it was in 2003 now. It's been a while. And it really sort of revolutionized our understanding of star formation in many ways. And I think because of that experience, I was very eager to work on the James Webb Space Telescope. And so I did a couple of postdocs, and when Space Telescope was beginning to, assemble teams to really seriously do work to develop Webb, they invited me to, come and participate, and I was, very excited. So I've now been at Space Telescope for, oh my gosh, I think it's almost 15 years, and it's been an incredible adventure.
Okay, great. Taylor?
Yeah. So when I was a kid, I actually wasn't very interested in astronomy. I very oddly had a dream of wanting to become an Egyptian mummy. And I don't really know why that is. So there's no good reason. But I discovered when I got to middle school that I actually really enjoyed math. And only because it was kind of like puzzle pieces, and you put them together and you get some interesting answer. And so I thought, okay, I need to do math. And then I got to high school, and I was introduced to physics for the first time. And I was like, oh my gosh, this explains the way things work on the world. That's really cool. And it uses my favorite parts of math. I was doing physics, and I went to college for physics. And then in college, I went to this small liberal arts university in Texas called Southwestern University. And there were 3 physics faculty. One of them happened to do astrophysics. And he's like, hey, you want to come help with the observatory? I was like, yes. And then from there, I was hooked. And I got introduced to the world of astronomy, and I kind of fell in love with it. After that, I went to graduate school at Texas A&M University. And from there, kind of got to know, oh, there's this really cool telescope that might launch soon called JWST. And it's going to be awesome. And it's going to first galaxies, the thing you're doing. It'll make it so much easier. And so when I was getting time to apply for jobs after I got my PhD, I applied to this NASA postdoctoral fellowship, and I ended up getting it. So now I work at NASA with Dr. Jane Rigby, who is the project scientist for JWST, and it's every single day is just such an adventure, and it's very fun, and I do not regret any decision that I've made along the way.
Okay, great. So I guess we'll start off with Brian. So I'm intrigued to learn more about the outer solar system. So what can Webb teach us about the Kuiper Belt and the Oort cloud?
Okay, yeah. So the size of the mirror of James Webb is very well suited for studying these objects that are very far away, very faint. And even obtaining spectroscopy. Others have talked about spectroscopy so far. Obtaining spectroscopy of these very faint objects, which is something that cannot be done from the ground. And by expanding the full amount of light that we can see, we're able to detect, with these light fingerprints, right, the spectra. We're able to detect different molecules on these objects. So, for instance, on some objects, we've identified ethane. It is a hydrocarbon. It's a processed hydrocarbon. It's a compound that exists on Earth, but it's an ice out there. And we're seeing those kinds of materials for the first time, right? I don't know if a detection has been made yet, but I expect one could be soon for other hydrocarbons like propane, right? I think you have experience with propane, right? We just, 4th of July was last week, so you probably, if you grilled, you might have used some propane, but it's an ice out there as well. So there are a lot of these components that also make up organic molecules, right? That are found out there, and that's what we've been as we've been studying with the comets that come in or the objects that are currently out there 40, 50 times further away than the Earth is from the sun.
Very cool. Okay, another question. This time, let's go to Emily. So what are the percentages of planets discovered by JWST, gas giants versus rocky planets?
Yeah, so most of the planets that, I don't know the exact percentage, but most of the planets that we look at with JWST are typically gas giants. And this is part of the reason for this is it is just easier to look at those than it is smaller terrestrial planets. You know, gas giants are much more massive, they're much brighter, and so it just makes it a far easier job for us to either directly detect them using the imaging technique I described, or even with the transit technique, bigger planets are easier to find because they produce a bigger dip in that light in the transit technique. And so we are also targeting terrestrial rocky planets, like our own sort of planet Earth, for example. But there is some observational bias that it is easier to find and to look at gas giants than it is rocky planets. But we will be looking at rocky planets too.
Okay, awesome. Let's go to Christine. So could you talk a little bit about why cosmic dust is so important for star and planet formation?
So that's a really interesting question. So when we think about how we get to planetary systems, essentially stars start off as the stuff in between stars. So they're basically clouds of dust and gas in between stars, and those clouds are the sort of places where stars form. The stars, basically you can get little regions that are over densities in here. And they start to collapse to form stars. They're spinning and it supports a disk. And so that's the basic physics. But that initial cloud that you start from is made out of both gas and dust. It's 100 times more gas than it is dust. But these dusts are like silicate particles that are a fraction of a micron in size. And then there is a really big problem in understanding solar systems in that, like, how do you get from those little tiny dust grains up to full-size planets, right? And so there are many theories that have been developed to address different size ranges of this problem. So first from sticking of little tiny grains, to van der Waals forces, like sticking bigger and bigger things together. But eventually you reach sort of a meter barrier, and we don't quite yet know how you hop over, like, getting things bigger than a meter. But then once you get to like even larger things, we know that by collisions, again, you could have elastic collisions where things stick together and they continue to build up until you get to like a Pluto-sized object. So in the protoplanetary disk phase, the collisions are constructive. You build things up that are bigger and bigger. And then in this later phase, the gas dissipates. And so it's more like our solar system where the bulk gas is gone. And so the collisions become destructive. And so now you're taking the asteroids and the comets, and when you smash them together, you break them up into little pieces. And those little pieces are really valuable because you can do remote sensing on them. And you can get a ton of detailed information about those little pieces. So you can measure their exact chemical composition, the size of the little particles, like their shape, whether or not they're fluffy, like just all sorts of things.
Cool. Okay, for Taylor, the farthest galaxies found by Webb were formed 390 million years ago, about after the Big Bang. So what features are the most interesting in these galaxies?
Yeah, so I'm a little biased. I'm a spectroscopist, and so I care about the light fingerprint that I described before. And so JWST is powerful for a lot of different things, but I think one of the things that really makes it this powerhouse of an observatory is its spectroscopic capabilities. And so it has 4 different instruments on it, and these instruments all have different kinds of light that they can look at and the different ways of spectroscopy. And I think the most exciting parts about these really, really distant galaxies that we're finding is not only seeing the images in such clarity and in resolution we've never been able to before. Like, they used to be fuzzy little 2-pixel dots, and now they're fuzzy dots that have much more pixels. So we can see if there's two galaxies actually merging together at these high distances. Or we can see structure of, the clumpy morphology of like different types of star forming regions in a single galaxy. And I think the imaging is very beautiful, but the spectroscopy is the part that's most exciting. And so we're seeing with these light fingerprints, the chemistry inside of these galaxies, like I was saying. And so you're able to really pick apart, like, okay, what's driving this bright light that we see in this galaxy? Is it what kind of stars? Are the stars in binary systems? How massive are they? Are they 100 times the size of our sun? And are there black holes inside of these galaxies? How big are the black holes? Let's figure all of this out. And so that's the most exciting part to me.
Awesome. Okay, so I'll throw this open to anyone who wants to answer, and I think it's a good question. So one question that we got are, why are all the planets round? Or why are they all spherical?
I guess you might be looking at me. Well, solar system planets, we can see, like we can image them, we can visit them, right? So we can, they're not just dots as they are farther away. Hopefully someday you'll be able to image some of the exoplanets as well. But planets are round because of gravity. So there's enough mass in a planet to make it into an equilibrium shape. And that shape is, in most cases, a sphere, or rather an oblate sphere, right? Anything that's rotating is going to be kind of distended. So the poles are squished in, and it's and around the equator it's bulging out. But we do notice other equilibrium shapes in the solar system, such as ellipsoids. So think about like a rugby ball or a football shape, right? American football with less points, right? So a rugby ball. It's still in that kind of equilibrium shape, but there's less mass, so it's not as spherical.
Okay, great. Thank you. So another question about the observatory is the level of debris hits in line with our expectations so far? I think this is people wondering about micrometeoroid impacts.
Yeah, I can take this or start to take it. Yeah, so we did expect, my understanding is that we did expect some amount of debris to be at L2 because it is a stable gravitational point in space in the Earth-Sun system. But the amount was concerning, and I don't think we really could have anticipated that until we threw a big telescope that was not protected by a dome of metal. The mirror is completely exposed, and that's kind of the first of its kind in space. So actually, it's something that we now have to do when we plan for observations with this telescope is astronomers are like, I want to look at this part of the sky. And then, the Space Telescope Science Institute and the people who control the telescope are like, okay, but only at this time of the year because we can't look into the fire hose of meteorites. And so we're looking away from it the whole time, trying to protect the mirrors. And so there was some expectation, but not this amount was a little bit alarming.
So. Okay. So another question, and this is for everyone. What is the most important advancement in science we can hope to achieve with JWST? That's from Dina T. from the Bishop Planetarium in Bradenton, Florida.
I can try and address that as a science policy person at Space Telescope. So what I would say is that JWST is an amazing observatory. And one of the reasons why it's an amazing observatory is because it's a flagship mission. And so it addresses all areas of astrophysics. And so, and it's sometimes when we build and fly new instruments, we make serendipitous discoveries that we did not anticipate when the observatory was first conceived. So, for example, the science case that Taylor talked to you about, like studying the first stars and galaxies, that was actually the killer app science case for building JWST. So that was the reason why JWST was built. And, it takes a very long time for flagship missions to come to fruition. And so, in between when they started the project and, when it launched, there was this realization that, oh my gosh, like transiting exoplanets, we can see that and we can study like their atmospheres in like exquisite detail. And so there was a lot of effort made to enable the observatory to be able to address those observations. Similarly, originally JWST was not envisioned to be a facility to study the solar system. The solar system part of planetary science part of NASA pitched in extra funding so that we could track solar system objects. So, I think it's really hard to pick like one specific thing that JWST is going to do. I would just say that I think our expectation is that it's going to revolutionize all areas of astrophysics, which is, I think, exciting for all of us.
Okay, I think that's a great answer. Okay, another question, this one about galaxies. Maybe Taylor can chime in on this one. Do we know how many galaxies there are in space? And how many has the James Webb Space Telescope photographed?
Wow, that's a
from
question.
Yeah, sorry, that's from Juliet at the Fort Collins Museum of Discovery in Colorado. Go ahead.
Yeah, thanks, Julia. That's a fantastic question. The answer is inconclusive. There are so many galaxies, but just to kind of give you an idea of scale. So the Hubble Ultra Deep Field, which is just this portion in the sky, it's incredibly tiny, that we had the Hubble Space Telescope stare at for, I think, 25 days or something. That tiny little portion of the sky ended up having thousands upon thousands of galaxies inside of it. And JWST has already looked at many, many fields and continued to increase the amount of imaging that we have and the tallying of galaxies. And so the numbers are incredibly high, especially across all distances of the types of galaxies. Millions and millions of galaxies have been found. And I forgot the second part of the question, but...
Oh, how many galaxies are there, and how many has JWST observed?
Oh, yeah, okay. Yes, so just in general, how many are there? Many, 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 many billions. Like so many galaxies. There's so many galaxies in the universe, which is really exciting. It means that we'll always be finding more and always be finding more beautiful things in space that we can find and discover. JWST has begun to start trying to map this, but it would take a very, very long time, even with that amazing observatory, to see all of the galaxies that exist. And so it's a really exciting, but yes, it's a very large number.
Cool. Okay, while I have you on, Taylor, I will ask you one more question because there's lots of excitement about early galaxies.
Yeah.
Can you describe how scientists determine the age of galaxies in deep field images? That's from the Dome Planetarium in Peoria, Illinois.
Yeah, that's also a great question. One of the ways that we do this is I was describing the light fingerprint before and how spectroscopy, and really the concept of that is the electromagnetic spectrum. And we're looking at a certain portion of light from that full spectrum. But there's so much light that is even past what we can see with our human eyes. And if you look at, a place in the sky for a really long time with different kinds of light, so you're using different kinds of telescopes, not just JWST, you're using the Hubble Space Telescope, ground-based telescopes, anything you can, looking at that patch of the sky for a very long time. And then you look at each of these different wavelengths of light and see where does something pop up suddenly as you go to larger wavelengths. And the further you go in larger wavelengths before something pops up, that gives you an indication of how far away something might be, because that's the first light that you see from it. And we call this a redshift or photometric redshift. And so this gives you an idea of how far away something is. And so the further and further away the photometric redshift is, or how far away something looks like it is, that gives you really good insight into what time in the early universe did this source exist? Like how far away is it? And then you track that with, how long did it take the light to get to us? This is how early the universe must be for where this galaxy is located. And that's kind of how, to the first order, how we kind of place an age on these things. And then when you get spectroscopy of them, you can get even more detailed and get a much more precise distance measurement, which gives you a much more precise time measurement as well.
Okay, great. Another question, this one about planet formation. If different molecules preferentially land at certain orbital distances, does this potentially increase the incidence of Earth-like planets?
So I think what the question is referring to is that when we look at our solar system or any region around a star, there's sort of like a temperature difference. As you go away from the star, it becomes cooler and cooler. And so it means that you can have different kinds of materials at different distances. So, so this refers to, like, for example, one idea that's very important to the formation of Jupiter and Saturn in our own solar system is the water ice snow line. So this says that basically, if you get too close to the sun, all of that water sublimates, is not available in solids to accrete into planets anymore. And so it's one of the explanations for why Jupiter and Saturn are kind of where they are, was that you had to have enough mass in the disk to form big planets, and you get helped if you boost the amount of disk mass by having water in solid form. But there's actually snow lines not just for water ice, but different ices as well. Carbon dioxide, methane, CO, I forget the exact condensation sequence. And so one of the ideas that people do have is whether or not they can look at, for example, the atmosphere of a giant planet and see, by looking at its atmosphere, what its carbon to oxygen ratio is, and then trace it back to where it was located, like where it formed. So that's one way to try to tie to formation location. I'm less aware for the terrestrial planets because, you know, again, we just get this atmospheric information, and it's hard to really know what the bulk density is to be able to tie it precisely to where it formed. I don't know if that helps.
Okay. I think that's a good answer. Another question, and this one is very popular, and maybe we'll go through and have everyone give their answer. So we are just finishing up 1 year of Webb Science, and we're just about to, or we have just started the second year of Webb Science, the cycle 2 observations. So the question is, what are the upcoming scheduled observations that you are looking forward to the most? And maybe we'll start with Emily, because we haven't heard from her in a while.
Yeah, I can go ahead. Sorry, I accidentally turned my speaker off for a second there. Yeah, so I am really excited about some of the exoplanets that we're going to be looking at, for which we have really precise mass measurements of. And so for a lot of exoplanets, we don't actually know their masses. We use models to interpret what their mass might be based on, like, how bright they are, for example. But for some exoplanets, we can use different techniques combined together. So not just imaging, but other techniques using ground-based observations, for example, to actually determine their masses. And once we know their mass, and we can get these really high-resolution spectra using JWST to really hone in on their atmospheric properties. And so we have a number of these exoplanets for which we have their masses, which are model-independent masses, and we're about to get these high-resolution spectra and really assess what their atmospheric properties look like and know their mass. And they're going to be some of the most well-constrained exoplanets that we have, and I'm really, really excited to learn more about these exoplanets.
Okay, great. Maybe Brian can go next. What are you excited about in year 2?
So in year 1, there was an amazing image of Enceladus, one of the moons of Saturn. This is an object that was detected to have water ice coming out of it at the South Pole area by the Cassini spacecraft. And it was observed by James Webb in cycle 1. And they're able to detect a very large plume, so much larger than Cassini could see in reflected light. So by looking in the infrared, they're able to see the water coming out at and extending thousands of miles away from the ejection area. And there are follow-up observations planned to map more of that area and see exactly how far this plume extends from the object, and how it feeds the ring, the Saturn's E ring. So the material coming out is forming a whole ring around Saturn. So we'll get some more information on that and see just how big it actually is.
Okay, great. Christine, what are you looking forward to in year 2?
Absolutely. We were looking earlier at the image of Fomalhaut and seeing how a planet can particularly impact a disk. But I'm interested in turning that question around and understanding how dust and asteroids and comets can affect planets. So one of the outstanding questions in our solar system is how the Earth acquired its water, which we all know is really important for the existence of life here. And this is a really hard question to address because although we've observed thousands of exoplanets, we've never seen liquid water on their surfaces. And so we don't know whether or not life like ours exists on those planets. And indeed, just detecting liquid water on planets is very, very hard. And it's so hard, it's something that JWST will probably not be able to do. But one thing that JWST can do is detect water in dust and asteroids and comets and try to catch it before it arrives on planets. And so in that way, I'm really looking forward to understanding, what is the potential for water in terrestrial planets and around other stars, and by extension, how did water get to our planet Earth?
Okay, and finally, Taylor.
Yeah, so honestly, what excites me most is we might find in cycle 2 or the second year is really what have we not expected that we're going to find, what kind of weird science thing that, we had these expectations of the kind of science that we get from this telescope. We've described quite a bit of it tonight in this panel, but what weird things are we going to find with this amazing observatory that kind of change the way that we see the universe? And I feel like this has happened with every major advancement that we've had in astronomy, especially with space observatories that we put up in space. So I'm really excited to see what that is for JWST. And I do think that there's a high chance that we'll find it in the second year, now that we have, all the things figured out this first year, as far as calibrations and stuff.
Okay, great. So we have just a couple minutes left. And I guess maybe another question for Taylor while I still have you. Have we gained any insights into dark matter in the first year of Webb operations?
Yeah, that's a great question. So we're starting that way. We're making good progress. I think one of the ways that you can kind of study the effects of the matter we can't see is through fields where you have lots of gravitational lensing, or this kind of a warping of light around big massive bodies. And this can be entire clusters of galaxies creating this warping of light. And if you study this in big scale and then also in small scale of individual galaxies warping light, you can really start to kind of see, okay, how are the things that with light that we see, how is this impacting this warping of light, but also the things that we can't see. And this does really help contribute to these equations and things that people are using to try and understand dark matter. So I think we don't have an answer yet, but I think this is definitely helping to push towards this in tandem with other observatories that are coming online as well.
Okay, I think that might be our final question. So I would like to thank all of our panelists again, Christine Chun, Brian Holler, Taylor Hutchison, Emily Rickman. So I am Kelly Lipo. I'm an outreach scientist at the Space Telescope Science Institute, and I hope that all of you at the community sites across the country and anyone who's watching this recording learned a little bit of what the science of what Webb has been up to in the past year, and you're all excited for the second year of Web Science and all of the cool, weird, wonderful things that it will find. So thank you, everyone, and I hope you have a great evening.